Thanks everyone for joining this OsmoDevCall. This time it's going to be about power control. I already presented here before, a long time ago, but in case someone of you doesn't know me, I'm Vadim, working for Sysmocom as a freelancer remotely. And it's almost 2 years now since I joined Sysmocom. Time flies quick. This talk is going to be about power control, specifically power control in GSM, and even more specifically power control implementation in the Osmocom radio access network stack. And as a bonus, I will also talk about 2 new features we introduced while working on the power control. That's BCCH carrier power reduction mode and temporary H overpower, 2 new features. So Wikipedia defines power control as an intelligent selection of the transmitter power in order to achieve good performance within the system. But what in general one needs to know is the goals of power control. That's a reduction of the average power consumption, which is important on the mobile station side. You don't want to waste your battery, and reduction of the co-channel interference, which is super important for the network providers, especially with the tight spectrum reuse. So power control is actively used in several areas. That's cellular networks, GSM, LTE, UMTS, and so on. Also in sensor networks, also wireless local area networks and personal area networks. We all know this as Wi-Fi, Bluetooth, maybe some more. And I also read in Wikipedia that DSL modems also employ power control. I have no idea and never had a DSL modem. So maybe Harald knows more about this. There generally exists 2 types of power control implementations. The closed power control, where the power is managed by the remote side. This type of power control is used in both in GSM for both MS and BS power control. In case anyone is not familiar with the terminology, MS is the mobile station, basically the phone, and BS is the base station, the cellular tower. Another type is the open power control loop. That's something I'm not really familiar with. I only know that it's used in GPRS. And the key point here is that power is managed autonomously without not necessarily employing the two-way communication between the transmitting sides. So for GSM, there exists 2 power control loops. Both are closed power control loops. One is the uplink power control loop or MS power control loop. And the other is the BTS or downlink power control loops. Both of them are executed simultaneously and independently, while the uplink power control is mandatory for both MS and the BTS. Downlink power control is optional. So for the uplink, it's basically BTS telling the phone to transmit at a higher power or lower power. And for the BTS, it's basically MS reporting the signal quality parameters to the BTS, and then BTS changing the transmission power based on that. And in both cases, RX level and RX quality is used as the input of the power control loops. So in case of the MS power control, there is always two-way communication via SUCH. That's one of the channels in GSM. For the downlink, it's not necessarily. There is only one-way communication, basically MS reporting the measurements to the BTS. And it's actually a very slow, relatively slow power control because period of such transmission is like half of a second. And compare this to 1500 times per second in UMTS, the power control is executed in GSM. It's only 2 times per second in the best case, and it can be even slower if you use the higher power control interval values. The problem here when we started to work on this is that unlike many other things, the exact algorithm is not defined by 3GPP. Neither the exact power control parameter list. So that was another problem. Only one of the specs briefly mentions some parameters, but there is no exact definition of how to transfer them, how to only recommended values for some of them and value range, but not the exact algorithm, unfortunately. Before we go into that further, there are 2 types of power control in GSM. Also, there's a static power control where the network allocates channel with a specific transmit power level, and it never changes after that, regardless of the channel quality. And there is also dynamic power control. This is the where the power control loop is involved. It takes RX level and RX qual measurements as the input, and then produces required TX power for either for the local side or for the remote side. So in both cases, you signal some TX power level during the channel allocation, and then after that, it depends on the type of power control, whether it's changed or not. And 3GPP defines general requirements for power control implementation, just like with the PCU packet control unit. 3GPP gives us freedom of implementing it either BSC collocated or BTS collocated. So similarly, in this case, the power control is performed either by BTS or BSC. But it's logical that power control parameters are configured in the BSC and then sent to the BTS over the ABIS link if necessary, if the power control is performed by BTS. That's, as I said, 3GPP gives us too much freedom here, so it's a vendor-specific encoding of parameters, no exact definition of information elements and so on. And this is how the MS power control loop flow looks like. I can make it a bit bigger for some time. So initially the MS sends, actually the MS periodically sends uplink such blocks. That's a slow associated control channel where it indicates the current transmit power level. And based on that, the BTS or BSC, that's called BSS in this case, either of those, it takes the control power control decision. So based on averaged and filtered uplink RX level or RX quality samples. And the required new transmit power level is signaled back to the MS, also via such channel, downlink such in this case. And the MS, when the MS receives this, it applies the transmitted power, and in the next block, it indicates the new TX power that was applied. So that's even slower than half of a second. With BTS power control, the diagram might look a bit more complicated, but actually it's a lot simpler. So BSS is sending downlink data. MS performs measurements of downlink data and sends the measurement reports on dedicated channel. And based on that, the BSS performs power control decision and adjusts the transmission power on its side. So after that, it's sending downlink blocks with either decreased or increased power level, or keeps it if it's sufficient. So for the input of those power loops, I already mentioned two major parameters. One is the Rx level, that's basically signal power, and normally it's in dBm, like the lower is worse. And GSM, for at least for measurement reports and some messages, defines reduced encoding of that parameter. That's from 0 with only 64 unique values. And yeah, all values exceeding this range simply map to the boundaries. For the Rx quality, the range is even lower. It's only 8 unique values. And unlike the Rx level, where like the value is 0 means bad and 63 means best quality. In this case, it's vice versa. 0 means perfect channel conditions, no or insignificant interference, and 7 means like worst possible conditions. And the criterion for this parameter can be either beta rate or the carrier to interference ratio. It depends on availability of the later. Like if carrier to interference ratio is available, it's preferable to use it because it's a better channel quality measure. This is how the measurement samples look like on the wire. Maybe make it a bit bigger. In this case, it's a measurement report on the ABS RSL. That's the link between BTS and BSC. The BTS sends a combined uplink on the top and downlink on the bottom, in this case, measurements to the BSC. And you see here like two variants of Rx level, two variants of Rx quality in both cases. So what is this full and sub? I specifically wanted to clarify this because for some people this may not be clear. In short, this relates to DTX, which is discontinuous transmission, another feature of GSM. Basically, during the voice call, MS or BTS may employ this technology, and more specifically during the silence periods when either of the parties is not talking, the MS or BTS may temporarily disable the transmission to save power again and to reduce interference. But you cannot just disable power for unspecified amount of time, because you still need to send pings to the base station to show that you're still alive, and same in the opposite direction. So 3GPP defines some special blocks with specific frame numbers that still need to be transmitted, regardless if it's DTX, if there is no speech at the moment, or you can the MS may send silence indications during that time. Basically, some parameters for the comfort noise encoding, and the sub values reflect measurements for TDMA blocks on those mandatory specific blocks, excluding the gaps in transmission, while the full is usually represents the full measurement period, including the gaps. And when looking at those parameters, there is a simple rule. If DTX is in use, then look at the sub parameters because they exclude gaps. And if it's not in use, look at full. This is how power control logic, general power control algorithm looks like. 3GPP defines, as I already mentioned, some limited set of parameters, mostly the thresholds for the measurements and the step size for increasing and decreasing power. So if we look on the right side of this slide, the perfect state of power control loop is in the middle, the white area in the middle. And if we reach, there is this on the x-axis, there is Rx level, which is the higher, the better. And on the epsilon, there is Rx quality, which is the lower, the better. So if we have poor Rx quality, regardless of the Rx level, we always increase the power. If the quality is good enough, but and at the same time the level, the signal level is high enough, then we decrease power. There is also transitional states and some magic to avoid ping pong between increasing and decreasing every so often. But what 3GPP gives us is the Rx level upper and lower thresholds, and for the Rx quality also upper and lower thresholds, plus some recommended step size values. But what's important here is the increase step is always bigger, should be ideally bigger than decrease step, because if you lose connectivity to the mobile station, let's say, you want to quickly increase the transmission power to try to recover the channel. And for reducing power, it's vice versa. You don't want to use it too quickly. You start either reducing by 2 decibels or by 4 decibels. And this nice picture is from interference reduction. That's a nice paper by Nokia Siemens Networks, which is unfortunately not publicly available, but can be found in Google. That's really a nice read. It helped me a lot when implementing the power control stuff. So regarding the state of implementation in OsmoBSC and in OsmoBTS, there has been major improvements by Sysmacom back in 2020 and 2021. Before that, we had a very limited power control loop in OsmoBTS, and all parameters were in OsmoBTS 2. That wasn't super handy, so now we moved all power control parameters back to where they should be, and deprecated the power control parameters in OsmoBTS. Also, there used to be no BS power control. This was also implemented during that time period. And for OsmoBSC, so far it only implements MS power control loop, while OsmoBTS implements both MS and BS power control loops. In late 2021, Keith imported some code from OsmoBTS. But unfortunately, our documentation still states that OsmoBSC does not contain any logic. So ideally, this should be addressed. So we should improve documentation. If you look at BSC telnet, if you connect to the telnet interface and look at the running config, you will notice that power control is already enabled for MS power control. It's already enabled if you are using NanoBTS or OsmoBTS. It's enabled by default, while BS power control is not. Going further into this rabbit hole of configuration parameters, we basically have 2 nodes with similar set of parameters, one for MS power control, another for BS power control. And currently, it's a configurable peer BTS node. We may want some maybe fallback or default parameters peer network, because if you have, let's say, 16 base stations, you don't want to copy paste the same configuration over all 16 nodes in the config file. That's an idea for potential improvement. And regarding the power control modes currently implemented in OsmoBSC, you have static mode. So that's what I explained a few slides before. That's you basically tell some initial power control value and then never change it after that. It remains constant. There is dynamic power control performed by BTS, and another type where dynamic power control performed by the BSC itself. And for if you want to employ dynamic power control and don't know what to choose between both 2 and 3, options 2 and 3, it's basically depends on what your BTS is capable of. If it implements the power control loop, then it's probably a good idea to enable this power control loop and run the power control logic in the BTS itself. So this way you can save some bandwidth on the ABIS interface. You don't want to see messages sent every 2 times per second for every subscriber, for each subscriber setting the new power control level. And another reason, yes, if as far as I know, RBS models, Ericsson RBS, they do not implement BS power control, so that's why Keith introduced power control loop to the BSC. So the most common parameters for the MS and BS power control, regardless of the node you are in, that would be the power control interval. That's number 1 on this screen. It basically allows you to intentionally suspend the power control decision. You keep measuring, but postpone the TX power level decision for later to basically stabilize the power control loop. I will talk a bit about this one a bit later. There is step size for increase and decrease. There is RX level threshold, RX quality thresholds, and number 5 is 2 parameter groups that we do not implement so far. You can see, you can check the 3GPP document 45008 for more information on how to use them, how they are supposed to be implemented. So far, we don't implement them. Our implementation is relatively simple. Of course, you want averaging for the input parameters, because otherwise you will be affected by small fluctuations of both parameters. This is not what we want. And until recently, there has been no averaging at all, until we started to improve power control back in 2020, 2021. And so far, we implement only Osmocom specific sliding average that's called EWMA, exponentially weighted, I don't remember, something averaging, moving average, as far as I remember. That was a long time ago. So you can also disable averaging completely. That's not recommended, because maybe only for testing, that's what we do in our TTCN3 tests, but definitely not recommended for production use. 3GPP also defines 2 parameters related to the measurement, to the averaging window. That's number 2 in this case, HREQV and HREQT. They are not used by OsmoBTS 2 at the moment, unfortunately. That's ideas for potential improvements. And also 3GPP gives us 3 algorithms that can be used for averaging. We don't implement them either. The scope was limited to this simple sliding average. That's Osmo EWMA. For MS power control, there are specific set of parameters. Like I mentioned before, you can, as the criteria for RX quality, for the quality of received signal, you can use either the bit error rate or the CI, which is the carrier to interference ratio. It's not CNR, signal to noise ratio. That's a different thing, although it's related a bit. And here you have parameters related to the CI processing, like thresholds, also similar to what we have for RxQual and RxLevel also. For the BS power control, we have only one specific parameter, that's the BS power. So either you set it to static or dynamic. By default, it's static, so no BS power control, because currently only OsmoBTS, as far as I know, can implement can work with our implementation. That was tested, and also I'm not sure if NanoBTS works. Probably needs to be tested. So you specify the power control mode here, and you specify the limit of power control reduction. In case of BTS, the BTS is transmitting at the maximum power level initially, and for specific channels you can decrease this power level depending on the input measurements from the MS. That's the value that you can specify from 0 to 30 dB. For the MS, we don't have this parameter because it's a bit more complicated. The maximum MS power is reported by the MS itself. That's MS power class in the class mark, but you still can limit the maximum MS power value using this MS max power parameter, which is not part of this new configuration blocks. It was introduced a long time ago, so ideally it should be deprecated and moved to the proper place for together to all power control related parameters. So I mentioned this power control interval already. This is basically intentional delay for the power control decision. I mean, we enable it by default for MS and BS power control loops. Basically, if the value of this parameter is 0, then the power control decision is taken every half of a second. If it's 1, then it's almost 1 second of delay, and so on and so on. So it basically determines the amount of such block periods to be skipped for the power control decision. But during that time, you still average and measure the samples, average the measurements. So regarding encoding of MS and BS power control parameters, again, this freedom of 3GPP, it's up to the BSS vendors. So far, OsmoBTS and OsmoBSC, we support, OsmoBSC so far supports only IP access and OsmoBTS. There are some Osmocom-specific extensions on top of that. And unfortunately, we don't have full Wireshark dissector yet. So if you look into the pickup with RSL traces, you will see just TLV with unknown octet string. And Wireshark does not know how to decode this. And so when the parameters apply, like let's say you finish this boring configuration stage, it also depends on the power, how the power control parameters are signaled to the BTS. If the power control is performed by BTS itself. For some vendors and models, it's RSL. The power control parameters shall be present in the RSL channel activation message, in every RSL channel activation message. And in this case, if you change something in the OsmoBSC configuration, the changes apply immediately for all newly allocated channels. For IP access NanoBTS, it's a bit different. There is a vendor-specific message that is sent in the beginning of the RSL bootstrapping. And this message contains default power control parameters. And after that, you can simply send RSL channel activation messages with empty parameters, and they will fall. The BTS will fall back to default parameters you previously indicated to it. power control parameters, yeah. And OsmoBTS replicates this behavior. It also supports sending power control parameters only once. But we also have VTY and control commands for resending default power control parameters without the need to restart PTS. This is how it can be done via the VTY interface. You basically specify a VTS number and use the resend power control defaults. That's the command. And in case of the control interface, there is a special set command, which is, you need to specify, always need to specify arbitrary value because it's a set command. It always requires some value, but it's ignored in this case. So what's the current state of implementation? Well, it works. Some happy customers already using it in production. We got quite positive feedback so far. We have unit tests for both MS and BS power control in OsmoBTS. We also have TTCN3 testing coverage. That's conformance testing. Some test cases mentioned here. We also some test cases are still in Gerrit, unmerged, unfinished. Maybe something to have a look at if there is any commercial interest in this again. What's missing at the moment is support for BS power control in OsmoBSC. I mean, when the BS power control is performed by the BSC itself. We only have MS power control so far. We also lack support of the RX-qual and RX level threshold comparators. And we don't support 3GPP defined averaging algorithms I mentioned before. Also, potential improvements I found in this amazing paper by Nokia Siemens Networks. They describe something called adaptive power control parameters, where the values of power control interval and power increase-decrease step sizes are not fixed, but dynamically adjusted depending on the current situation, like interference levels and so on. Yes, adaptive, that's what I mean. But, there is also another interesting topic that's service-dependent power control. Like with AMR, it's the key benefits of using AMR is that it's robust against interference, sometimes even more robust than signaling in GSM. So for AMR, it might make sense to have different profile of power control, different set of power control parameters, maybe for CSD, circuit switch data also. There is also enhanced power control and enhanced measurement reports. I'm not really familiar with this technology, but as far as I know, in enhanced power control, the power loop is reacting quicker. It's reacting with the interval of 100 milliseconds. It's basically every burst rather than every block. There is also enhanced measurement report. We don't implement this at the moment. There is also power C flag in the system information messages indicating if the BS power control is currently in use or not. I remember reading some recommendations regarding enabling or disabling it. It's not like you can simply enable it if you use BS power control, because there are downsides of that, as was observed on practice. So this needs to be investigated further. And power control in GPRS, that's the open power loop, something that I'm not really familiar with. We definitely need to improve documentation in this regard and maybe add VTY parameters if there are none at the moment. So two additional features I promised to talk about, additional to the power control, that we can also consider them power control. There is a BCCH carrier power reduction mode of operation. So 3GPP states that BCCH carrier shall transmit continuously without gaps, even if there is nothing to be transmitted. Then in this case, dummy bursts are used as the filler. PS by default is not permitted on the BCCH carrier. For BCCH carrier, as the name suggests, is the TRX of a BTS that has the BCCH and CCCH channel, just to clarify. And the idea of this feature that was not allowed before version 13 of this document is to allow constrained power reduction on some time slots of the BCCH carrier up to 6 decibels, and for all time slots except those carrying the BCCH, and also limited for time slots preceding them. You can have BCCH on time slot 0, but as far as I know, you can also have it on additional time slots. So time slots preceding them should be also reduced not more than 2 decibels. The goal here is to save power on the BTS side, but this comes at a price, because this reduction of power negatively affects cell reselection and performance for the MS, and handover failure call drop rates also increasing when it's enabled. So the idea is that you don't enable it by default, and we don't enable it by default, but you may want to enable it during the night, let's say, when the amount of subscribers is lower. So again, 3GPP does not specify the exact signaling here. Asmacom came up with a vendor-specific extension to the aerosol. That's basically pretty standard aerosol BS power control message, but with the channel number information element indicating BCCH. That's a beautiful hack. And at the moment, only OsmoBTS supports this hack at the moment, and specifically the OsmoBTS TRX variant. I don't know if it's even possible to regulate downlink power on the DSP-based models like OsmoBTS. That's so. How does this play together with the PS power control? It's should be noted that it's not the same. It's not BS power control loop. It's a static reduction for inactive time slots. So actually, or subchannels of the time slots, while BS power control applies to active channels only. By default, BS power control is disabled on the BCCH carrier unless the BTS is operating in this power reduction mode. In which case, BS power on active channels can also be reduced up to 6 decibels, regardless of what the power control, BS power control configuration states. This is how to configure, how you can configure BCCH carrier reduction in the VTY. That's the VTY of OsmoBSC. It's basically just a maximum value for maximum reduction value in 2 decibel steps, and you can also trigger it via the control interface using control commands. Another feature that we recently implemented, that's the temporary edge overpower. So this is a special technique for improving such and fudge performance. Such is slow associated control channel, fudge is fast. You always have such, but you have fudge only during the voice calls on TCH channels. I'm not sure, maybe also during CSD calls. The key idea here is to increment the transmit power on the BTS side by 2 or 4 decibels, only for flash or such bursts, but not for the normal voice bursts. And this feature is useful for deployments with tight free frequency reuse, and specifically useful when using AMR codec, which, as I already mentioned, has flexibility in areas with high interference. It's much more robust than normal encoding like TCH-FR or HR. Again, this is not standard feature. This is something we learned from a nice book that will be mentioned later. It is enabled by sending OsmoCon-specific information element in the RSL channel activation messages, disabled by default again, and only OsmoBTS TRX is supported at the moment because, again, we don't know how to control downlink power on the DSP-based models. Maybe there is a way. I don't know. That's behind the scope of my work when I worked on this. And this is how to configure this feature, Hatch Overpower. You can selectively enable it either for fudge or for such, or for both of them at the same time. And you have a threshold that's a beta rate threshold. I don't remember if a carrier to interference ratio can be used for that. As far as I remember, no. So when the quality reaches this threshold value, then the overpower is automatically enabled by the BTS. And when it's back to normal, BTS automatically disables overpower. You can also specify for which channels BTS can employ overpower. It's useful by default. It's only for AMR channels, but can also be enabled for any other. This is an example of configuration in OsmoBSC. In this case, for both such and fudge, the RX quality threshold is 4. So when the beta rate is higher than 1.6%, then this is the overpower is enabled. And in this case, it's only for AMR codec. That brings us to the end of this talk. Thanks for listening and thanks for joining. This presentation is available online. You can see the link here. Also, we have quite good, I would say, documentation for the power control and for both mentioned features, power control and for overpower and for BCCH carrier power reduction. There are 2 interesting papers. Actually, not one of them is paper that's interference reduction. That's by Nokia Siemens Networks. You can find it in Google. And another is a book, quite a nice book recommended by Harald. We actually learned about the overpower feature and about the BCH carrier reduction from that book. So thanks, everybody. I'm happy to hear your questions. Well, yes, as far as I remember, Paul mentions that it might be interesting to note that MS does not need to support all MS power levels, and it should adjust the more nearby requested to what requested by the network. I don't remember all the details, but that depends on the MS power class. As far as I remember, the network shall not command values that are outside of the power class. It also depends on the band. If it's a GSM 900, you can have 33 dBm. That's almost 2 watts. And for, actually, it's vice versa, right? It's for 900, you have to 30 dBm, and for 1800, it's higher because the signal power gets lower.